This is the review for Calculus Quiz 4, or quiz, excuse me, test. This is the review before Calculus Test 4, and it is the review for Quiz 12, meant to prepare you for Test 4. All right, so we're working with general logs and exponentials. It says here, differentiate f of x log base 2 of 1 minus 3 to the x, a general log, okay, follows the same thing as a natural log to begin, so we take the original to the bottom, the derivative of that to the top, and then we take the natural log of the base, which is 2. All right, the next one, 38. Okay, this one's a lot trickier. This one has radical x to the x power, and this is kind of a difficult one. And the way we do this is we get this x off of the power. And anytime we have x stuck in a power and we don't want it there, we use natural logs. So I use natural log of y equals the natural log of radical x to the x power. Okay, and once I've done this, I can take this x out front. So now I can turn it into natural log of y equals x natural log of x like that. All right, and this is an okay way to start off the derivative. So now we've got in a position where I can just use the product rule on this side pretty easy. Okay, so let's do this side first. So I'm going to perform the actual derivative here. Now, what that says is take the original to the bottom and its derivative to the top. So I've got y prime over y. That's the derivative of the natural log of y. All right, and I'm going to end up solving for y prime. Next, I'm going to use the product rule on the other side. The product rule would go 1 natural log radical x, okay, plus x times the derivative of natural log of radical x. So we're going to go fraction, radical x to the bottom, and the derivative of radical x to the top. Okay, now at this step we should solve for y prime, which means move the y over to the other side. Okay, so when I do that, I'm going to have y prime equals y natural log radical x plus, and I'm going to do some cleanups here. Technically, this is a negative radical x, so I'm going to move it to the bottom. Okay, this is a half, so I'm going to put the 2 on bottom. I'm going to put the x on top. So I now have x over 2 radical x radical x. All right, one more time. The half is where the 2 came from. This radical x is already there, and this is a x to the negative half, which is going to join it on the bottom as a radical x. Okay, so another way we could do this, we could clean this up to x, and that would then cross off. Okay, so if I make this a regular x, because radical x times radical x is x, I can cross off those x's and just make this a half in this location. Another thing is that sometimes this y is replaced back with what it is equal to. So that would look like this. Y prime equals radical x to the x power multiplied by natural log of radical x. Let me take that out. Natural log radical x plus a half. There we go. So this piece is kind of hard to read, so I'm going to rewrite it. Natural log radical x. There we go. For this question, because it is a complicated function to a complicated function power, it's not an exponential, so really we're going to try to get this natural log out of being the power. The way we do that is with logarithms. And if I apply a log to both sides, so if I log the left and I log the right, what that will allow me to do is bring this natural log out front. So the power inside of a natural log, because technically all of this is inside of that natural log right there. So what I have now is I can take this power from the inside out front of the natural log. So this natural log of x is going to go in front, and then it multiplies by the natural log of sine of x. So that's what allows us to actually do the derivative now, because this is no longer a power, so I've removed the problem. Now this looks like a product rule. So on the right hand side I have y prime over y because the original goes to the bottom, and the derivative of that, y prime, goes to the top. On the other side I have, let's take these derivatives one at a time using product rule. So the derivative of natural log of x is 1 over x, and I leave the other one in its original state. I plus, now I put natural log of x, and because this natural log of x reflects this staying in its original state, and now it's this term's turn to do a derivative. So the natural log sends the sine to the bottom, and the derivative of sine, which is cosine, to the top. Now cosine over sine we could write as cotan, and I'm going to do that. I'm going to switch that to cotan, and I'm going to multiply the y over to the other side. So really this y is in front of everything, plus natural log of x cotan x. Okay, and many times we go back to the original, and instead of having it in terms of y here, we want everything in terms of x. So it's going to most likely be written like this. So we take that y and we replace it by what y equals. And because y equals sine of x to the power natural log of x, that's what would go here. Power natural log of x multiplies by 1 over x natural log sine of x plus natural log of x times cotan x. All right, and that one is done. All right, next. What I'm going to do here is use a product rule. Okay, so y prime. And the 4 power x is like e to the x. So it starts off with its original self. Then we multiply by the derivative of the top, which is 1. Then we multiply by the natural log of the base, which is 4. So all of that right there is the derivative of 4 to the x. We leave the 5 to the sine of x alone. Okay, and now I'm going to put a plus sign, and now I will reverse course and leave the 4x alone. And now it's 5 to the power of sine of x that we are going to use the derivative of. So I'll put that in parentheses just so I'm consistent. So we start off with just like the original times the derivative of the top, that's a cosine x, multiplied by the natural log of 5. Again, the reason we have these extra natural logs of the bases in here is because it's not e. It's an exponential function, it's not base e, so we have to do natural log of the base. All right, and that's good enough there. There's no reason to clean that up any further. Okay, so this is the graphing calculator section right here. It says consider this equation, f prime equals this. For x is this. When is x increasing and decreasing? Find the inflection points for f. All right, so let's use a graphing calculator analysis on this one. Okay, so I'm going to type all of that into y equals, and that is log base 10, so I'm good on that one. X math 3 minus x plus 1, close. All right, and I'm going to turn off this right here, and I'm going to put 0 in. I'm looking at the derivative. I'm thinking first derivative test analysis. So I want to know where this is above and below the x-axis. So not bad. All right. And they only said for x greater or equal to 0. So it looks like trace 0 gives me 0. All right. And it looks like 1 is the other place. That's pretty clear. So 0 and 1 are the places where it zeroes out. We are under it, then over it. Okay. So just as a basic analysis here, what I have at 0 and 1, okay, are the places where we have critical points, because again the derivative equals 0 there. We were under the x-axis, so we are decreasing. We are over the x-axis, so we are increasing, and this is f prime, this is f. So to answer the question, is decreasing, we should say f is, on the interval from 0 to 1. And f is increasing on x greater or equal to 1. Here we go. Okay, the inflection points. The inflection points are going to be the derivative of that. So I could do the derivative by hand, and I could actually look at that, or I could turn this one off, turn on the derivative of that, and let's get a sketch of that. All right, and this one didn't, well, I guess in the original problem they said focus on x greater or equal to 0, so that's all I'm going to focus on as well. And we need to actually cross the x-axis. So what I'm looking at here is f double prime. This is the second derivative. And we can see it go from negative to positive at this place right there. It looks like it's a half. Let's try it. And it is. Okay, so I have a point at 0.5. All right, so I can see just a little bit of an analysis here. At 1/2, 1/2, we have f double prime switching from negative to positive, so f switches from concave down to up. All right, so we have an inflection point at x equals a half because f double prime changes from negative to positive. All right, next, the slope of the tangent line to this graph at this point is what? All right, so I'm going to have to find the derivative of this and plug in this point. So that's what I'm looking for. I'm looking for the rate of change. All right, the derivative of natural log of x is 1 over x. The derivative here is going to be 2e to the y times the derivative of y, it's y prime, equals 1. Now I have y and x to plug in. The x is going to be a 1, and the y is going to be negative 0.693. So 1 over 1 plus 2e to the negative 0.693 y prime equals 1. This is 1 over 1. I said 1 and wrote x. Okay. All right. Now, when I actually take this and that divides to 1, and when I subtract it over to the other side, I'm going to have 0. All right. So I'm going to be left with 2e to the negative 0.693 multiplied by y prime equals 0. And when I divide, I'll end up with y prime equals 0. All right, next it says let f be the function given by this function right here. For what values of x is the slope of the line tangent to the graph of f at this point equal to this? So I'm looking for where is the slope equal to that. There's two ways to do it. One way would be to do the derivative and actually then set that equal to negative 2.3 and solve. Another way to do it is to use the graphing calculator and guess and check. Okay, so when I say guess and check, I mean try the 5 values. So I would type in the original, okay? I can go e to the 2 divided by x. Now I can graph that, and I can use the calculate menu to find slopes along the curve. That's what I'm going to do. Or I can turn that off and turn on the derivative and then just trace to the different values and see what they are. So that might be a little faster, but this is a little bit simpler. Okay, so 3, I put in the original function, and I'm going to graph it on zoom 6. Just give me a little zoomed out view from what I just had. All right, now I want the slope, second calculate 6 at my first value, negative 1.168. And I'll be done if it gives me negative 2.3. It does not. All right, next, second calculate 6 at 1.276. Nope, not right. Okay, second calculate 6, 2.318. So I'm trying option C. And it's close. All right, let's try D. Second calculate 6, 2.438. And there it is. Got it. All right, next, find the inflection point on this. Write your answer in perfect form, no decimal approximation. So I'm going to stay away from the calculator for a little bit, and I'm actually going to try to find this by hand. So first, f prime of x equals e to the x minus 2x. Next, the second derivative is going to be e to the x minus 2. I need to know where that is equal to 0. E to the x minus 2. All right. And solving for x here means I'm going to move the 2 over here. I'm going to natural log both sides. Okay, so x equals that. Let's do a number line analysis. So, okay, natural log 2 is 0.7. So I'm going to compare that to 0.5 and 1. All right. So let's try 0.5. And because we're doing a second derivative test analysis, comparing that f double prime to f. Okay, if I take 0.5 and plug it into the second derivative, let's see what we get. Okay, second e to the 0.5 minus 2 is negative. Okay, second, e to the 1 minus 2 is positive. Okay, so we go from concave down to concave up. All right, and therefore we have an inflection point there. Second way to look at it, okay, I've got e to the x minus 2, and just graphing it. Okay, I can see it go from negative to positive, and it does that. So I can calculate at, I'll need that trace at the natural log of 2. Here we go. Okay, explanation. X equals natural log of 2 is an inflection point because f double prime changes from negative to positive, and I just put it a little bit more, so f changes from concave down to up. Here we go. Okay, let's do our application questions, get those out of the way. Okay, a curve passes through 0, 5, has the property that the slope of the curve at every point P is twice the y coordinate of P, which means that y prime slope equals 2y. All right, what is the equation of the curve? All right, so what I'm going to do now is I'm going to integrate. And in order to integrate, I want to get the y prime and the y on the same side. So I don't want to have y's left over and y primes also left over. So y's in multiple places doesn't help me out. Now, if I just move this y over to the other side, now it makes it much easier. Okay, here's why it works. The natural log of g of x has a derivative, okay, that has g prime over g. And I'm recognizing that I have the derivative on top of the original, so if I integrate on both sides, I'm going to have the natural log of the absolute value of y equals 2x plus c. Actually, I know what I'm going to do next, so I don't want the plus c yet. Okay, now to solve for y, I'm going to perform e on both sides, so what I call e it up. When I do that, I'm going to have y equals e to the 2x, and when we have these functions, we put the c in front. Now I'll take the x and y. So now I use 0, 5, which is x and y. I'll have 5 equals c e to the 2 times 0. Okay, and this is going to create a 1 because it's going to be e to the 0. So that's 1 times c, so 5 equals c. Finally, restate your answer. 5 e to the 2x. Got it. Okay, 19 says, the rate of change of the atmospheric pressure P with respect to altitude h, that is dP dH, okay, is proportional to P. That means there's some multiplier K times P. All right, another way to say this is P prime equals K P. All right, provided that the temperature is constant. All right, and at 15 degrees Celsius, we're not going to use that because that has to stay constant in order for this to work. The pressure is 101.3 at sea level. So we have an ordered pair now. The ordered pair there is going to be pressure, that at sea level, 0, 101.3. Okay, so in order to help start finding these things, what I'm going to do now is I'm going to move the P over to the other side. So I'm going to have P prime over P, the same pattern we saw last time, equals some constant K. All right, when I actually integrate both sides, I'm going to have the natural log of P equals KH. Okay, remember that we did with respect to H here. Okay, so another way to say it is that we have H and P. So when I do the integral on the other side, I have to do so with respect to h, and this becomes kh. Now I perform an e on both sides, and I have a c in front. Okay, so I have these unknown values that I'm just not sure what they are. Now, I have to use both ordered pairs in order to help me find them. Okay, so when I plug this one in right here, okay, so use the second ordered pair, I'll write down H and P was 1000 and 87.14. Okay, so I'm going to use the first one. Use 0, 101.3. When I do that in this equation, I'm going to have 101.3 equals C e to the k times 0. So all of this goes away, and now I know that 101.3 equals C. Because it's 0 power of e, that creates a 1 in this location. So I just have 1 times C equals this. So there, we found part of our answer. Okay, so now we're at P equals 101.3 e to the kh. Now I'm going to use the second ordered pair, 1000, 87.14. When I do that, I'm going to have 87.14 equals 101.3 e to the k times 1000. So that's where we are right now. And I'm going to divide both sides by the 101.3. Okay, so when I do that, 87.14 divided by 101.3 gives 0.86. Okay, now I'm going to natural log both sides. Okay, and then I'm going to divide by 1000. So k equals natural log of 0.86 divided by 1000. And I'm going to have an enormously small number of negative 0.12315. Okay, final answer. It wasn't Y, it was pressure. It was pressure equals 101.3 e to the negative 0.00015 h. And that is our final answer. That one's pretty tough. All right, let's look at number 5. It says at time t equals 0, the temperature of a hot pocket is 200 degrees Fahrenheit, and the room temperature is 72 degrees Fahrenheit. The hot pocket cools according to the differential equation, d of capital T with respect to little t, so it's temperature with respect to time, equals negative 1/3 the temperature plus 24. All right, find an expression for T of t using the initial condition T of 0 equals 200. All right, so first thing I'm going to do is I'm going to try to get all the capital T's on the left and all the little t's on the right. So I'm going to use this function right here, and I know I'm going to be dividing and moving things around, so I can move the dt, the little dt, over here, and I'm also going to do a trick where I make this fraction come out front. So I'm going to have negative 1/3 parentheses t minus 72 dt. So I really did two things. First, I multiply the dt over to the other side. Okay, and I know I'm going to divide by this right here, and rather than keep the negative 1/3 and have to deal with it in the denominator over here, I just chose to factor it out. And when I do that, I have to be able to multiply it back in. So this has to be a negative 72. So when I multiply by negative 1/3, it recreates positive 24. So I factored out the fraction piece, and I'm going to leave that on the right so that the piece I actually divide by is just the t minus 72. dt equals negative 1/3 dt. All right, so now it's in a form where I can do the antiderivative of both sides. So when I perform that operation, I'm now going to have the natural log of t minus 72 equals negative 1/3 t. All right, now, one more time. The reason that I factored out the negative 1/3 is I would have had to deal with it, and it would have made a difference in my antiderivative at this point right here. So from here, I'm now going to solve for capital T. So I'm going to have to e both sides. When I do that, I'm going here this way. Okay, so I'm going to have t minus 72 equals e to the negative 1/3 little t. All right, and when I do that, I should put a c out front. And I'm going to move 72 over to the other side. So I have t equals c, my starting value, e to the negative t over 3 is how I'm going to choose to write that, plus 72, because I moved this 72 over to the other side. All right, so c out front goes with all these types of equations, so that is kind of my starting value, just like we have plus c at the back. In these functions, though, we have plus c, capital C right there. So it's really the initial condition on the exponential. And rather than writing negative 1/3 t, I just put the t up top, so it just looks a little cleaner. All right, now I need to find the actual value of c, and I'm going to use this in order to find that. So I know the temperature is 200, that's capital T, and I go C of basically 0, because I'm going to have 0 divided by negative 3, all right, plus 72. And I'm going to subtract 72 over to the other side. That's going to give me 128. And C of 0 is just 1, so that equals C. Now let's actually state the answer. 128 e to the negative t over 3 plus 72. All right, and there that is. So that's the answer to part A. The input is time, the output is going to be temperature. All right, that's pretty tough. Okay, next it says find the limit as t approaches infinity. And I could just take a really big number and plug it in for t, and I'm going to find it goes to 72. It also makes sense because room temperature is at 72, and our value is going to come down at a decay function towards that room temperature. So the limit as little t approaches infinity on cap T, little t, 72. All right, how hot is the hot pocket at the time when temperature is decreasing? Okay, so we're looking at when the rate is decreasing at 10. Okay, so here's my rate function. So I'm really using t prime equals negative 1/3 t plus 24, and I have negative 10 over here. So negative 10 equals negative 1/3 capital T plus 24. Just solving for capital T, I'm going to subtract the 24 over to the other side. That'll give me negative 34 equals negative 1/3 capital T. Multiply both sides by the negative 1/3, and I'm going to end up with 102 degrees Fahrenheit. Okay, this was also degrees Fahrenheit. All right, at what time did this occur for part C? All right, so time and temperature are related in this function that I found up here. So I know that I've got my temperature of 102, 128. I have e to the negative t over 3 plus 72, and I have to solve for little t. I'm going to subtract the 72 over to the other side. When I do that, I will have 30. Now I'll divide by the 128, my goal being to isolate the e so I can natural log it, but I want to get this 128 over to the other side as well. So when I do that, when I take 30 and divide by 128, I'm going to have 0.234. Okay, now I'm going to natural log both sides. Okay, so the natural log of that answer is negative 1.45. And I natural log both sides, so now I have basically t over negative 3. Let's do it that way. Multiply that by negative 3, and it would occur 4.35 minutes. All right, and it says minutes. All right, and that's our answer to all of that. Okay, for 39, first thing I see is the tangent negative 1. all right, of x. And the way I'm going to approach this question is to do the derivative of the arctan of x. The derivative of arctan of x is 1 over 1 plus x squared. All right, so I take that inside and I square it. So what I'm using there is this arctan rule right here, and it says g prime over 1 plus g of x squared. So the inside basically gets squared. All right, and that equals 1 plus 3y squared y prime. And in order to solve for y prime, I'm just going to have to move these things away from that. So first I'm going to subtract 1 over to the other side. 1 plus x squared minus 1 equals 3y squared y prime. Okay, and now I just need to divide by the 3y squared. So when I do that, I'm going to create, let's see, there's a couple ways I could do that. Probably the easiest is just this way right here. 3y squared, 1 over 1 plus x squared minus 1 equals y prime. Okay, so it's not pretty, but there's a lot of ways you could do that. That's one. So first, can you get to the knowing the derivative of it is that. Okay, next we have sine of x over this term right here. Okay, and I also ask what is the average value of this function. All right, so let's keep it going. And what I'm going to recognize, right now we're doing an integral of that, so something creates this on the bottom. And sine is the derivative of cosine, so we're going to use the exact same rule we had here. And if I just say that the antiderivative is the arctan of x, okay, just think about that for a second. The inside of the arctan is x. It gets squared on the bottom, and the derivative of it goes to the top. Now, if I make it the arctan of cosine x, then what's going to happen is that the cosine gets squared in this location and the derivative of it goes to the top. And we are super close to that working. So the only difference is that this right here is positive and the derivative of the cosine would be negative. So there we go. So now I have my antiderivative. So just recognize that this right here is that. All right. The next thing I'm going to do is apply my limits of integration. 0, pi over 2. Okay, so at this point I have negative arctan of the cosine pi over 2 minus a negative, so it pluses, the arctan of cosine 0, and let's see what those are. So in this case, I have negative second tangent cosine pi over 2 plus second tangent the cosine of 0. And I have 0.7853. All right, and just double check. That is pi over 4. So you could say it's pi over 4. All right, next one. Okay, I'm looking at this, and I'm looking through my list of arc sines and tangents and stuff like that, and I have a radical. So with a radical, I'm probably going to be an arc sine or arc cosine. And the question is, in this right here, I'm looking at these two. Okay, so we have 1 minus g squared in the inside on both of them, but the arc cosine has a negative in front of the derivative on top, and this one does not. Okay, so I've got a negative in front of the derivative on top. So first, here's how I'm looking at this. Okay, and then here we have basically, if I did a derivative, I would have 3t squared. Okay, so the derivative here would be 3t squared. Now I don't have the 3, and what I have to figure out is it going to be the arc sine or arc cosine? They're basically the exact same thing, where the arc cosine is the negative version of it. So I'm just going to go with the arc sine. okay? And the arc sine has an input of t to the third, and I need to make this 3 go away, so I have to put 1/3. 1/3 arc sine t to the third plus c. Okay, so how do I know it works? Okay, so I know it works because the radical on the bottom made it so that it was either going to be an arc sine or arc cosine. So I know that some value is squared here, so the value that I'd square there would be t to the third. Okay, so that gives me my t to the sixth. The derivative of this piece would be there, which is 3t squared, if it is an arc sine. Okay, and to make this 3 go away, I have 1/3 in front. Don't forget plus c on the back side. All right, the next one, it says find the derivative of f of x equals e to the x cosh of x. All right, and the cool thing about the cosh, the hyperbolic cosine, is that its derivative is sine, and sine's derivative is cosine. All right, so this is going to be a product rule. E to the x is its own derivative, and I'll just have cosh of x plus e to the x, and the derivative of cosine hyperbolic of x is sine hyperbolic of x. Here we go. All right, next, the tangent hyperbolic is going to be 1 minus the tangent hyperbolic squared g of x times the derivative of the inside. So here we go. F prime of x equals 1 minus the tangent hyperbolic, okay? And again, it said that that value is supposed to be squared, tangent hyperbolic of x of the inside multiplied by the derivative of the inside on the outside. So that's going to be half x to the negative half. This one is e to the cosh of x of 3x. Okay, so what I'm going to do to find y prime is I'm going to know that e is its own derivative, times 3x, multiplied by the derivative of the top, which is sine hyperbolic 3x, times the derivative of the 3x, which is 3. And that one then is done.